Statcoms, also known as static synchronous condensers, have been a part of power system engineering since the early 1990s. Their topology and operating principles were documented as early as 1992, marking a significant evolution in reactive power management. These devices were developed to address the limitations of conventional reactive power solutions, both passive, such as mechanically switched capacitor banks MSC and reactors MSR, and active, like thyristor switched capacitor banks TSC and reactors TSR. Unlike these older technologies, Statcoms are capable of responding to fast-changing reactive power demands and highly dynamic loads with precision and speed. The term synchronous in Statcom refers to its ability to generate or absorb reactive power in real time, synchronized with the grid's voltage and frequency conditions. This synchronous operation allows Statcoms to stabilize voltage levels effectively, making them indispensable in systems where reactive power demand fluctuates rapidly. Their real-time responsiveness ensures that voltage remains within acceptable limits, even under challenging load conditions or during disturbances. Statcoms are versatile and can be deployed across a wide range of medium and high voltage applications. Their benefits are particularly evident in installations with solar inverters, wind turbine generators, transmission and distribution networks, hydrogen electrolyzers, railway electrification systems, and industrial setups with large motors or low power factor loads. In these environments, Statcoms help maintain power factor, support voltage stability, and reduce energy losses, especially where reactive power demand changes abruptly or in large steps. Functionally, Statcoms deliver both inductive and capacitive reactive power with high accuracy and speed. This dynamic capability allows them to outperform traditional solutions like capacitor banks, shunt reactors, and synchronous condensers, which often suffer from slower response times and mechanical limitations. Modern Statcoms also integrate multiple control functions, enabling them to address power quality issues, provide ancillary grid services, and support the integration of clean energy sources, all within a single compact device. In the context of overhead distribution lines, Statcoms play a critical role in maintaining grid stability. As demand for electricity grows and regulatory and environmental constraints limit grid expansion, existing transmission and distribution lines are pushed closer to their operational limits. This stress increases the risk of voltage instability, especially in areas with large concentrations of inductive loads such as induction motors. One common issue is fault-induced delayed voltage recovery (FIDVR), where system voltage remains abnormally low for several seconds after a fault is cleared. This phenomenon can lead to significant load losses and even cascading failures across the grid. FIVR, fault-induced delayed voltage recovery, is particularly problematic in regions where single-phase, low-inertia induction motors are prevalent. During faults, these motors stall when voltage drops below 0.8 per unit, drawing excessive reactive power up to 5 or 6 times their normal operating current. This surge in reactive demand further depresses system voltage, prolonging recovery times and risking widespread instability. Since disconnecting these motors for extended periods can cause substantial financial losses, system operators require a solution that can stabilize voltage without interrupting service. Statcoms offer that solution. When installed along overhead distribution lines, especially near problematic inductive loads, they can inject reactive current rapidly during and after faults. This fast response helps restore voltage levels quickly, mitigating the effects of FIDVR and preventing voltage collapse. Beyond fault recovery, Statcoms also contribute to reducing transmission and distribution losses, enhancing overall system efficiency and reliability. Statcoms are a cornerstone of modern grid management. Their ability to deliver fast, precise reactive power makes them essential for voltage regulation, power quality improvement, and fault resilience. As power systems evolve to accommodate renewable energy and increasing demand, Statcoms provide the flexibility and control needed to ensure stable, efficient, and compliant grid operation. The working principle of a static synchronous compensator Statcom revolves around its ability to inject or absorb reactive power into an electrical grid to maintain voltage stability. This is achieved by generating a controllable AC voltage that is synchronized in frequency with the grid voltage, using advanced power electronic converters. The core of this system is the voltage source converter VSC, which transforms a steady DC voltage provided by a DC capacitor into an AC waveform that matches the grid's frequency and phase. The VSC typically employs high-performance semiconductor devices such as insulated gate bipolar transistors IGBTs or gate turn-off thyristors GTOs to ensure precise and rapid switching. To interface with the grid, the STATCOM uses a coupling transformer that matches voltage levels and facilitates the exchange of reactive power. A dedicated controller continuously monitors the grid voltage and dynamically adjusts the output of the VSC to either inject or absorb reactive power, depending on system needs. When the STATCOM's output voltage exceeds the grid voltage, it supplies reactive power to the grid, functioning like a capacitor. Conversely, when its voltage is lower than the grid's, it absorbs reactive power, acting like an inductor. If both voltages are equal, no reactive power is exchanged. This dynamic control allows the STATCOM to respond instantly to voltage deviations caused by faults, load changes, or other disturbances. By adjusting the magnitude and phase angle of its output voltage, the STATCOM helps restore grid voltage to desired levels, ensuring stability and compliance with operational standards. Its fast response and precision make it a vital component in modern power systems, especially in environments with fluctuating loads or high penetration of renewable energy sources. The integration of wind energy into modern power grids presents unique challenges due to its variable and intermittent nature. To ensure grid compliance and maintain system reliability, the installation of reactive power compensation devices such as STATCOM Static Synchronous Compensator or SVC Static Var Compensator has become essential. These devices offer fast, dynamic control of reactive power, which is critical for stabilizing voltage, supporting fault ride-through capabilities, and meeting the increasingly stringent requirements set by grid operators. One of the primary reasons for deploying STATCOM or SVC in wind farms is to manage voltage control and stability. Wind power output fluctuates with wind speed, leading to voltage variations at the point of common coupling PCC. Grid operators mandate that voltage levels remain within tight limits, typically plus or minus 5% of nominal voltage, to prevent instability. STATCOM and SVC respond rapidly to these fluctuations by injecting or absorbing reactive power, thereby stabilizing voltage and ensuring compliance with grid codes. Reactive power compensation is another vital function. Wind turbines, particularly Type 3 DFIG and Type 4 full converter models, often operate with variable power factors and may not inherently provide sufficient reactive power. Grid codes require wind farms to maintain a near unity power factor or offer reactive support under diverse operating conditions. STATCOMs and SVCs fill this gap by dynamically adjusting reactive power output, enabling wind farms to operate in fixed power factor or voltage control modes as needed. Modern grid codes also demand that wind farms remain connected during short-term disturbances, such as voltage dips caused by faults, a capability known as fault ride-through FRT. During such events, the PCC voltage can drop sharply, creating a surge in reactive power demand. Without adequate support, wind farms risk disconnection, exacerbating grid instability. STATCOM and SVC provide the necessary reactive power swiftly, helping maintain voltage and allowing the wind farm to ride through faults without tripping offline. Power quality is another area where these devices prove indispensable. Wind turbines equipped with power electronics can introduce harmonics and flicker into the grid, degrading power quality. Grid operators enforce strict limits on these disturbances. STATCOMs and SVCs mitigate such issues by smoothing reactive power flow, reducing voltage flicker, and improving the overall quality of electricity delivered from the wind farm. At low wind speeds, turbines may not generate enough reactive power to support grid voltage, leading to under-voltage conditions. In these scenarios, STATCOM or SVC can inject the required reactive power, ensuring voltage compliance even when active power generation is minimal. This capability is crucial for maintaining continuous operation and avoiding unnecessary curtailment. As renewable penetration grows, grid codes have evolved to demand more from wind farms. These include requirements for voltage regulation, reactive power control, fault ride-through, and fast dynamic response to voltage or frequency deviations. STATCOMs and SVCs offer the flexibility and responsiveness needed to meet these demands, making them indispensable for grid code compliance in regions with high renewable integration. In areas with significant wind energy penetration, grid stability becomes increasingly complex. Large-scale wind farms, especially those located far from load centers, can influence regional voltage profiles. Centralized reactive power compensation via STATCOM or SVC ensures that these installations do not destabilize the grid, supporting both local and system-wide voltage management. When comparing STATCOM and SVC, both serve similar roles but differ in performance. STATCOM offers superior dynamic response and excels under deep voltage sags, making it ideal for wind farms facing stringent grid codes. SVC, while slightly slower, remains a cost-effective solution where space and budget constraints exist. In conclusion, the deployment of STATCOM or SVC in wind farms is not just beneficial, it is essential. These devices stabilize voltage, compensate for reactive power deficiencies, enhance fault ride-through capabilities, and ensure compliance with modern grid codes. They also improve power quality and support grid stability, especially as wind energy becomes a larger share of the global energy mix. Their role is foundational in enabling wind farms to operate reliably and responsibly within the evolving landscape of power systems.